Okay, so before we define the derivative, let's go back to one of the first concepts we discussed in the last topic, and that was the average rate of change of a function over an interval. So recall that the average rate of change of the function f of x over some interval, and now I'm going to write the interval in a little bit different way. I'm not just going to write a to b. I'm actually going to write a to a plus h, where h here I'm just thinking about as being a positive number. Okay, so I'm just kind of parameterizing the interval by its length. Okay, so h is the length of the interval, and of course the interval is starting at a. And if I just let h equal b minus a, which is the length of the interval, you see that this really is just a to b. Okay, so don't think too much about that. But over this interval, the average rate of change of the function is just f of a plus h minus f of a all over h. Okay, and notice again that I'm dividing by the length of the interval, which is b minus a, but I'm saying v minus a. Maybe I'll just put that down. So b minus a, I'm thinking about as h, based on how we defined average rate of change before. And so just to note, this is the slope of the secant line between 2 points on the graph of this function. So between the points a and f of a, and then a plus h, and f of a plus h. Okay, and of course we have this nice picture of the secant line. So we have the function f of x, and then the secant line. So this is a, and over here is a plus h. Then the secant line just connects these 2 points. Okay, but of course we're also interested in the instantaneous rate of change. And in fact, that's going to be a little bit more useful for our applications. So we're really looking for the tangent line at x equals a. So the average rate of change is over an interval. So here's our interval. The instantaneous rate of change, or what we'll call the derivative, is going to be at a point. And so what we're going to do is we're really going to let this h go to 0 and watch these secant lines level off to the tangent line, assuming that our function has a derivative at that point. Okay, so now that we've sort of reviewed, and I keep saying this word derivative, let me actually tell you specifically what the derivative is. All right, so the derivative of a function at x equals a. So notice the difference between average rate of change and what we're defining here. The average rate of change is over an interval, and the derivative is at a specific point. It's an instantaneous rate of change. So the derivative at x equals a is given by, well, it's basically this same difference quotient that we had for average rate of change, but again, we want to let that h go to 0. And the whole reason we went through this process of talking about limits is to have a way to precisely say h is getting closer and closer to 0. So we're taking the limit is h goes to 0. And now we introduce some notation. That's what this kind of colon equal sign means. So I'm going to define this notation to mean the derivative. Instead of saying f of a, well, that's the function value, I'm going to say f prime of a. So this is the derivative right here. So when you see f prime of a, all it is it's the limit of this difference quotient. So you're just taking those secant lines and their slope, the average rate of change, squeezing them in around some point x equals a, and that's giving you the derivative. Now, one important note is that this definition only makes sense if this limit exists. So a very important kind of caveat is that this is only defined if the limit exists. And for now, we'll just assume that this limit exists when we talk about its properties. So here we go. The derivative, what is the derivative? Okay, so I sort of just made up a vocab word, derivative. You know, it doesn't mean anything if I just say it. I need to tell you what it really is. The derivative is the instantaneous rate of change. As well as the slope of the tangent line. Okay, so again, if you want to go back and think about our velocity example. So the average rate of change was the average velocity of a position function over a time interval. But if you look on the speedometer in your car, that tells you the instantaneous rate of change. So actually, the derivative is that instantaneous speed that you're traveling, or instantaneous velocity. If you are thinking about, well, am I going forward or backward? But we'll talk about that later when we talk about applications. But this is what you need to know for now. The derivative, has this technical definition as a limit. That's how you actually compute it. If you want to figure out what it is. So if it's 2 or 5 or -3 or whatever it is, that's the slope of that tangent line geometrically. But its interpretation is that it's the instantaneous rate of change of the function. It's the slope, if you will, of the function, which of course is changing. So let me give you a quick sketch. So again, if we have a function, and we'll just kind of sketch it like this, make it sort of arbitrary, and then we have a point x equals a, somewhere right here, then our tangent line, assuming it exists, of course, assuming that limit exists, if that limit exists, then the tangent line exists. Okay, so here's f of x, our function. and then we have a tangent line. And we'll be a little bit more specific about what the tangent line is in a second. But the derivative, so f prime of a, is equal to this number m, the slope of the tangent line. Okay, so geometrically it's very clear what the derivative is telling us. And actually, if we want the equation of the tangent line, notice that for the tangent line, we have the slope, and if we want a point on the line, well, we know a point on the line. It's a comma f of a. Remember that this point is the point of tangency for the tangent line. It's the point where the tangent line just barely touches the function. So a f of a is a point on the line, so the tangent line really is y minus f of a, so I'm just using point slope form, equals m times x minus a. Or, if you prefer, I can add f of a over. So this is kind of the general form for the tangent line, right there. That's how you find it. So in order to find the tangent line, you need the slope by taking that limit, finding the derivative at x equals a, and then just using this point of tangency, a comma f of a, to find the equation of the tangent line. So the next thing we need to do is sort of go back to this question, does the derivative always exist? And of course, the answer is going to be no, because it's defined as a limit. And as we've already seen in our discussion on limits, limits don't always exist. So the derivative, f prime of a, does not always exist. But just to introduce some more notation or some more terminology, if the derivative exists, so if f prime of a exists, or in other words, if the tangent line exists of the function, or we'll see later if the function has what's called a linear approximation at that point. So if f prime of a exists, then f of x is what's called differentiable at x equals a. And now this is going to be more related to when we talk about derivative functions. But for now, we just want to introduce this terminology because it'll just kind of get thrown out. It's just in our mathematical language. The derivative exists, a function is differentiable, the tangent line exists at that point. There's just a lot of different ways to say the same thing. And probably that's why math is confusing. Well, that's why anything is confusing. If there was only one way to say something, then it would probably be easier to learn. But it wouldn't be as broad and kind of rich in content because there's all these different ways to think about the derivative or think about differentiability. But the key thing when you're learning this for the first time is to realize that all of these concepts are exactly the same thing. The instantaneous rate of change, the slope of the tangent line, the derivative, differentiability, they're all just saying the same thing. So let's get into the really interesting question of talking about when a function is not differentiable. We're going to spend plenty of time talking about functions that do have derivatives. That's going to be an essential part of this class. But we're defining this concept, and so it's going to be worthwhile to think about cases where the derivative does not exist. Okay, so when is a function not differentiable? Well, recall that the derivative is defined as a limit. So this question, when is f of x not differentiable, is the same as this question. When does f prime of a not exist? And when I say not exist, I mean as a limit, because this is a limit. Well, in order to answer this question, we got to think back to how can a limit not exist? Well, there's some really complicated cases that we're not going to consider. We're really just going to consider the simplest case, okay? When, as a limit, the left-hand limit doesn't equal the right-hand limit. So we're going to introduce some more terminology, but it's really nothing new. So we're going to define what's called the left-hand derivative, and if you're really tracking, you're going to know exactly what this is. It's just the left-hand limit of f prime of a. So instead of just taking the limit as h goes to 0, we're just going to take the limit as h goes to 0 from the left of this difference quotient. And then similarly, we'll define the right-hand derivative. So this is really nothing more than looking at the slope from the left and from the right. What is the slope approaching? If they're approaching the same thing, then this limit will exist and the function will be differentiable. Okay, so we need these two things to be equal. That's the key point. For f of x to be differentiable, well, the left-hand derivative has to equal the right-hand derivative. And in the first example, we'll see of a function that's not differentiable, that's exactly what we'll do. We'll look at the left-hand derivative, and we'll look at the right-hand derivative, and show that they're not equal, therefore the function will not be differentiable. Okay, so let's look at everybody's favorite function. Now, of course, I'm being sarcastic. I doubt this is everybody's favorite function. But the function we're going to look at is absolute value of x. And I'm just going to explicitly write down absolute value of x as a piecewise function to be very clear what it is. So recall that absolute value of x is just going to be x when x is greater than or equal to 0, but it's actually going to be minus x when x is less than 0. Okay, so here's the question. What is f prime of 0? What's the derivative of the function at 0? Or in other words, what's the slope of the tangent line passing through 0? Well, let's just sketch what this function looks like, first of all, just to kind of illustrate what the problem is going to be. So this function looks like this. It looks like y equals x going this way, but it looks like y equals negative x going this way. So if you look at all of these points, so like if you look at -1, then the slope is just going to be the slope of this line, -1. Or if I look on the other side, like at 1, the slope or the derivative is just going to be 1, right? Because these are just lines. They're just kind of put together in pieces. But what about at 0? What is the slope of this function at 0? Well, let's look at the two limits. Let's look at the left-hand derivative and the right-hand derivative. So the limit is h approaches 0 from the left of absolute value of 0 plus h minus absolute value of 0 all over h. Well, this is just the limit as h goes to 0 from the left of absolute value of h over h. Okay, but kind of saving, all of the steps, this is something we saw with limits. This is a one-sided limit. And because h is approaching 0 from the left, absolute value of h, we want to use this definition. So this is really minus h over h, or minus 1. And that really makes a lot of sense, because if you just think about the slope as you approach 0 from the left, it's -1, right? It's just a slope, it's just a line passing through the origin of slope -1. And then the right-handed derivative is going to be the same thing, except this time, when we look at absolute value of h, we're to the right of 0, so we're just going to use h. So this is really going to be h over h, which is 1. So the limit is just 1. And again, that makes sense, because to the right, our function is just y equals x, which has slope 1. So here, we say the absolute value of x is not differentiable at 0. But notice that actually f is continuous at 0. And this is something that we'll mention later, that actually being differentiable is stronger than being continuous. So in other words, if you're differentiable, then you will be continuous at that point. And another way to think about differentiability is what we'll talk about next. That differentiability is really talking about smoothness in some sense. So again, let's look at just kind of the geometric meaning of differentiability. So if a function is differentiable, then f is sometimes said to be smooth at x equals a. And this really goes back to the idea of looking at how a function is changing. If a function is differentiable, then somehow it's changing nicely there. It's just kind of accelerating or decelerating in some sense. There's not any sort of jerking going on. And so let's just look at a few examples of when a function is not differentiable and see the types of situations where a function cannot be smooth in some sense. So let's look at some examples. So one example we've already seen. That's when a function has what's called a corner. And that's the case like for absolute value of x. And so you see that a corner is not smooth, right? So if you kind of trace your hand along a corner, it doesn't roll kind of from one, it doesn't change and roll around the corner. It's sharp. It has a sharp corner, so it's not smooth. Okay, so sharp means not smooth. Okay. And again, we saw this by showing that the left-hand derivative doesn't equal the right-hand derivative. So if we kind of approach the corner from the left, we have a slope going like this, like if you look at the top of a house. Like if I go up one side, I have a slope this way, and I go up the other way, I have a slope this way, and they meet at a corner like that, then it's not smooth. Okay. So another example is what's called a cusp. And a cusp more or less is the same thing as a corner, but a cusp, instead of just kind of meeting at two different angles, a cusp really is coming down and smoothing out and then coming back the other way. So really, the left and right hand derivatives are becoming undefined. So the limits aren't existing, but somehow they're infinitely. So one is approaching infinity and one's approaching minus infinity. Not just, being left and right. So, from the left here you get a number, from the right here you get a number. They're not equal. Here you're really getting that the limit is an infinite limit, right? And so from the left, the slope is approaching minus infinity, and from the right, the slope is approaching infinity, is the idea. So this is really thinking about infinite slopes. Whereas here, in kind of a limit sense, here we're just thinking about those limits not being equal. And then the final example that we'll look at is what's called a vertical tangent. And this is similar to a cusp, except that actually there's some consistency in the left and right hand limits, that they're actually both either approaching infinity or approaching minus infinity. And so if our function looks something like this, so we go up and we see that our tangent line, the slope, is actually becoming undefined. So the tangent line exists here, but the slope is undefined. So tangent line has undefined slope. Or in other words, the tangent line is vertical. Hence the name vertical tangent. So actually the tangent line exists, but it's vertical. It has an undefined slope. So if you look at the left-hand derivative and the right-hand derivative, in this case they would actually both be approaching infinity. Whereas with a cusp, in one direction you're approaching infinity, and in another direction you're approaching minus infinity. So there's really not a well-defined tangent line in that case, just like with a corner. So you see, these are just three examples of cases where functions can fail to be differentiable, okay, or they can fail to be smooth in some sense. So these are just important to keep in the back of your mind, and in the examples we'll actually see specific cases where these come up. Okay, so our goal here is to find the equation of the tangent line of f of x passing through the point x equals a. So here, f of x is 1 over x squared, and we want the equation of the tangent line passing through the point x equals 1. So what do we need? So we're looking for the equation of a line. We need the slope. And the slope of the line is just f prime of 1. Okay? So the slope of the tangent line is just the derivative at x equals 1. So we need to figure out what that is, first of all. And then we need the point on the line, or any point on the line, to write down the equation of a line. But we know what that is. We're just going to use the point 1 comma f of 1. We're going to use the point of tangency. So we're going to use the point where the tangent line just barely touches the graph of the function. And this is actually just 1, 1, right? Because if I just plug in 1, I get 1. So the real question is, what is the slope? What is the derivative? That's the interesting question here. So let's just write down what the derivative is, or what the slope of the tangent line is. So it's the limit is h goes to 0 of, well, 1 over 1 plus h squared minus 1 over 1 squared all over h. Okay, so just in case you're a little bit confused where this came from, remember that the derivative f prime of a is the limit is h goes to 0 of f of a plus h minus f of a all over h. And so all I did here is just evaluate. So a is 1. I just evaluated f at 1 plus h, and then minus f evaluated at 1, and then divided by h. So this limit, as will most of the time be the case when finding a derivative via the limit, is going to be an indeterminate form. If I just try to plug in h equals 0, I'm going to get 0 over 0. So I'm always going to have to do more work. And normally that's going to involve just some typical algebraic tricks like we've seen before. So what I can do here is, well, get a common denominator. So this is 1 plus h squared. This is just 1. So I can write this as 1 minus 1 plus h squared over 1 plus h squared all over h. So all I did, this is just 1. I just wrote this as 1 plus h squared divided by 1 plus h squared. And then because I have a common denominator, I can just do the subtraction in the numerator. Okay, so what do we have here? Well, this 1 plus h squared, I can actually expand that out as 1 plus 2h plus h squared. And now I'm taking 1 and subtracting all of these values. So let's just do that. So 1 minus 1 is 0, and then 1, and then, okay, so 1 minus 1 is 0, and then we're subtracting 2h, so we're left with minus 2h, and then minus h squared. So this is a common mistake. So the temptation is to say, okay, 1 minus 1 is 0, and then just 2h plus h squared. But you got to remember that you're subtracting this entire quantity. So really, the negative gets distributed to all of those terms. And then divided by 1 plus h squared all over h. Okay? And I'll skip a little bit here. So the numerator of the numerator has a factor of h, as does the denominator. So I can actually cancel one of those factors of h. So I'm really just left with the limit as h goes to 0 of minus 2 minus h over 1 plus h squared. Okay, and now I can just evaluate. I can just plug in h equals 0, take the limit, so this is going to 0. So that's gone, and then that h is gone. 1 squared is just 1, so it looks like the slope is just negative 2. Okay, so the slope is negative 2. Then I just use my point slope form. So it looks like I have y equals negative 2 times x minus 1 plus 1, or I think that ends up being negative 2x plus 3. But we'll just leave it like that for now, because that is the equation of the tangent line. And you see the most important part is finding the derivative. Okay? So negative 2, we'll see a picture in just a second, is like the slope of that function at x equals 1. And of course I'll just write negative 2x plus 3 if you prefer slope-intercept form. So let's look at a picture real quick. All right, so here is the fruit of our labor. We started with this function, 1 over x squared, and then we were looking specifically at x equals 1. Here's our point of tangency, 1, 1. And so we know the tangent line is just going to barely pass through that point, but we needed to find the slope, right? So then we determined that f prime of 1 was negative 2, so that gave us the slope of the tangent line. Then we just used point slope form to find the equation of the tangent line, negative 2x plus 3. And the cool thing to do is to use some sort of computer algebra system and to plot the line and be amazed when, yeah, actually this line is tangent to the function. It's just barely touching the function at that one point. It's giving you see that if I look at the blue function, the slope of that function is it's changing. So it's starting really steep, and then it's kind of leveling off. And at x equals 1, the slope of the function is equal to the slope of the tangent line, which is negative 2. So it's telling us how the function is changing at the point x equals 1. Okay, so let's do it again. We had so much fun last time. So what do we need? We need the slope, which is going to be f prime of 0. So we'll figure out what that is. That's going to be most of the work. And then we need a point on the line to get the equation of the tangent line. And we're just going to use that point of tangency, so the point where the tangent line touches the graph. And that's going to be 0, f of 0, which is going to be 0. F of 0 is just 1. If I plug in 0 for x, I get 1. So there we go. So let's find the slope. Let's find the derivative. So f prime of 0 is just going to be square root of h plus 1 minus 1 over h. Okay, and so why is that? Well, I plug in a plus h for x, but a is 0, so I plug in 0 plus h, so this is f of 0 plus h. Let's just write that up here. This is f of 0 plus h, and then this is f of 0, but we already found that f of 0 is 1. Okay, so then I just subtract those two quantities, and divide by h. And again, if I try to plug in h equals 0, I'm going to get an indeterminate form. So I need to do more work. And if you recall with limits, we have a red flag here. We have a square root. So let's multiply by the conjugate. And let me actually not forget the most important part here, that really I need to take the limit as h goes to 0. That's important. Okay, so if I try to take this limit, like I said, I'm going to get an indeterminate form. So I'm going to multiply by the conjugate. So I'm going to multiply by square root of h plus 1 on the top and bottom. And in the top, that's going to give me a difference of squares. So that's just going to be h plus 1 minus 1 all over h times square root h plus 1 plus 1. And so again, this is just square root of h plus 1 squared, which is h plus 1, minus 1. 1 squared, which is 1. Alrighty, and so now, notice that the numerator, so this is 1 minus 1, so I'm just going to be left with h, but then that means these h's will cancel. And of course, again, in the limit, as h goes to 0, I can ignore h equals 0. And so what I'm left with is the limit as h goes to 0 of 1 over square root of h plus 1 plus 1. But now I can actually take the limit. So as h goes to 0, this becomes 1. So 1 over 1 plus 1 is 1 over 2. So the slope of the tangent line at x equals 0 is 1/2. Alrighty, but we have the y-intercept. So actually the equation of the tangent line is easy to write down. It's just 1/2 x plus 1, because the y-intercept is 1. When x is 0, y is 1. So this is the equation of the tangent line. And again, this is, a good bit of work to take the limit to find the derivative. But the cool thing about this is you get to see it. You get to actually see what you're finding. You're not just doing math, blah, 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 doing math just to do it. You're doing math, and then you get to plot it, and you get to see, oh my goodness, I'm actually finding something geometrically that's really cool. And you're going to see it has so many applications. So let's look at a picture. All right, so here it is. In blue, we have the function square root of x plus 1. And we were trying to find the tangent line at the point x equals 0. So that was 0, 1 on the graph of our function. And we found that f prime of 0 was 1/2. So the slope of the function in blue at x equals 0, it's leveling off. So it's starting really steep, the slope, and then it's kind of leveling off. And right here, it's 1/2. So it's really cool to find these slopes, to find these tangent lines, look at what's going on. We're really developing these tools to study how functions are changing. Okay, so let's bring in some devil's advocates to kind of shake things up. We're talking about these derivatives, finding the slope of the tangent line. Everything's great. But what about if a function is not differentiable at the point? So here we have this function g of t, t to the 2/3. And we want to determine whether the function is differentiable at the point. And so remember that differentiable, what does that mean? It just means that f prime, in this case of 0, exists. So we need to figure out whether or not f prime of 0 exists as a limit, okay? I guess I should say g here, right? Because it's actually g, not f. And you'll see kind of as we go along, we'll start mixing up the notation. We'll use different letters for the variables, different letters for independent variables, dependent variables, because in different contexts you use different variables. So here we're using g of t, so maybe t represents time or something like that. So for g of t, we want to know whether or not g prime of 0 exists. So let's just write down what g prime of 0 is. So g prime of 0 is going to be h to the 2/3, so really 0 plus h to the 2/3 minus 0 all over h. And so just a reminder, this is g of a plus h. This is g of a. And in this case, a is equal to 0. So I'll let you verify that. And of course, very easy to forget, we're taking the limit as h goes to 0. And it really is important, as you're taking these limits, to leave the limit. That's just good notation, it's good practice, it's good mathematical practice. It'll also help you get full credit on problems or partial credit on problems that maybe you don't get exactly right. It'll make your grader very happy if you use good notation. So you leave this limit until you actually evaluate the limit. So this is just the limit as h goes to 0 of h to the 2/3 divided by h. Or limit as h goes to 0. So h to the 2/3 divided by h to the 1st is the same thing as 1 over h to the 1/3. But this is something that we've seen before when we talked about infinite limits. So we know that the limit as h goes to 0 from the right of 1 over h to the 1/3 is going to be infinity, because we're dividing by a small positive number. But the limit as h approaches 0 from the left, now we're going to be dividing by a small negative number. So it's going to be approaching minus infinity. So what does this mean? G is not differentiable at t equals 0. And why is that? Because this limit does not exist. So again, we see this connection between does g prime of 0 exist and g not being differentiable at t equals 0. So both of these are, of course, equivalent ways to say the same thing. But the point is, this function is not differentiable. And actually, if you remember our discussion on cusps, this function g has a cusp at t equals 0. So let's see a picture. Okay, so here's a plot of the function g of t equals t to the 2/3. And we see we have a problem. This function is not smooth at this point. It has a nice sharp corner, but it's actually stronger than a corner. It's a cusp. And it's a cusp. We actually showed that it was a cusp because the limit from the left, as we approach 0, goes to minus infinity. Limit from the right goes to infinity. So it's really, really sharp. It's like if you put the ends of a piece of paper together and kind of bend it inwards, it kind of goes like if here's the piece of paper and I put the two ends of the piece of paper like that, they're meeting at a really, really sharp corner. That's kind of like a cusp, if you want to kind of think about where these occur naturally. And we see that if we try to find a tangent line through this point, we're going to be out of luck, right? So we see really, actually, we can almost argue that any line passing through this point could almost be a tangent line. And in fact, if you go on and learn more math, it's actually the case, it's not that a tangent line doesn't exist here, it's actually that there are infinitely many tangent lines at this point. So the tangent space really is the whole space instead of being kind of a one-dimensional line. It's actually just the whole plane. So, I mean, this is probably more than you signed up for, but the point is this function has what's called a cusp. You have infinite limits from the left and the right not equaling, and so it's not smooth. The derivative doesn't exist. The tangent line doesn't exist, or is not well defined anyway. It's not differentiable, etc. Instantaneous rate of change. We don't know what's happening, right? So we don't actually know how the function is changing at that point. It really could be doing a lot of different things. It could be just changing direction, or it could be, we really don't know. That's the point. We don't know how the function is changing at that point, at that corner or cusp. Okay, so let's look at one more example. This time we have h of r is equal to r to the 1/3. Again, at r equals 0. So let's take the limit. Now, this is going to be a little bit confusing, but not so confusing. As h goes to 0, of course this h is not the same as this h, but we're not going to explicitly use h here. But we're going to plug in h to the 1/3 minus 0 over h. And again, this is h of, well, here it is going to get confusing, 0 plus h, and this is h of 0. And this h is actually the limit h, and then this h is, of course, the function h. But the point is the limit is just equal to that. And this is h prime of 0. So this is really the limit, is h goes to 0 of h to the 1/3 over h. And very similarly to the last example, we can rewrite this as 1 over h to the 2/3 in this case. Okay, so what does this do? Well, what this does is, because this h in the denominator is being raised to an even power, as well as being cube rooted, we know that the limit as h approaches 0 from the right of 1 over h to the 2/3 is going to infinity. This is 1 over a small positive number. But actually the same thing happens as h approaches 0 from the left, because even though we're plugging in small negative numbers, they're becoming positive because we're raising them to the second power. So this is again 1 over a small positive number, so the limit is infinity. So actually in this case, now we're getting that the slope of the tangent line is undefined, but there's a consistency from the left and the right. So the limit from the left is infinity, the limit from the right is infinity, and what we'll see when we look at the picture is that this is a vertical tangent. Okay, so here's the graph of the function. H of r is r to the 1/3. And here we see this vertical tangent. And so it's a little bit interesting Because on one hand, you can see that this function is smooth. I mean, if I trace this with my finger, I don't feel any sharp points, right? It is smooth. But the problem is coming from the fact that to be smooth, my slope actually has to become undefined. So my slope at r equals 0, sorry, at r equals 0 is undefined. So even though the function appears smooth, the tangent line is vertical, so the slope is undefined, so the function is not differentiable. So to answer our original question, this function is not differentiable at 0. So it's a little tricky, but that's how it goes. Undefined slope, function is not differentiable, even though in some sense the function is smooth. But what we'll see is what that actually means is that the derivative function is not defined. So that's why it's not differentiable.